Chapter 6, Sample Problem Number 3. A person pulls a block across a rough horizontal surface at a constant speed by applying a force F at a slight angle as shown. A free body diagram is drawn from the block. The arrows in the diagram correctly indicate the directions, but not necessarily the magnitudes of the various forces on the block. A student makes the following claim about this free body diagram. The velocity of the block is constant, so the net force acting on the block must be zero. Thus, the normal force equals the weight, and the force of friction equals the applied force F. What, if anything, is wrong with this statement? And if something is wrong, identify it. If statement is correct, explain why. So, a couple things. One, the student is 100% correct that since the velocity of the block is constant, the net force acting must be zero. That's Newton's second law, or if you want, the first law, one or the other of those two, and that is certainly true. What that ends up saying in a vector sense is that we can say the sum of the forces, which from our diagram is, well, we have Fn, and we have the weight, and we have the force we pull at, and we have the frictional force. Those are our four forces, and that has to equal ma, and that has to equal 0. So that would have been a correct statement of the second law. Where the student goes wrong, where the student has made a mistake, is that F does not act along any of these directions. So I can start saying, I might end up breaking them up and saying, well, let's take force F, and let's break it into an Fx and an Fy part. And then I can break each of those things down further, and I can say, well, then Fn, the force Fn, is just Fn in the y-hat direction. And the weight is just F sub g in the minus y-hat direction. And the force, which is what we just did here, is going to be Fx in the x-hat plus Fy in the y-hat. And then Fk is going to be its magnitude, but in the minus x-hat direction. And now we can gather up people who have the same unit vector. So I'm going to gather up everything has an x. So I'll have Fx in the x-hat. And then I'm going to have a minus, minus Fk x-hat. And that will be it. And then, of course, I'll also have Fn in the y-hat. And I'll have a minus Fg in the y-hat. And I'll pick up a plus Fy in the y-hat. And then I'm going to do stupid algebra tricks. I'm going to factor out the component vectors. So then I would have, when I factored out an x-at from these guys, I would have an Fx minus an Fk. And then over here, I will factor out a y-hat, and I'll have Fn minus Fg and then adding back in Fy. So we can see that F isn't directly opposed to Fk, and so it can't exactly cancel out Fk. It's more complicated because of the angle. All right, the algebra here just shows us, because what we end up saying is that we have that our net force is equal to 0 x-hat plus 0 y-hat, because the acceleration is 0. And that lets us take the x-hat and y-hat parts separately and say them equal to each other. So together that ends up telling us that we have Fx minus Fk is 0. And separately, Fn minus Fg plus Fy is also going to be 0. But we don't get the simple equality the student said, because of the difference in directions. The real key thing here is always remember is that you can't really compare things until they're in the same direction. And if they're not, you can only compare components that do lie in the same direction.